Okay, thank you for coming. So this is going to be an exciting talk. We're going to be talking about the fastest machine learning in the world with GPUs. GPUs are sexy exactly for that reason, that they allow you to not wait around too long. So think about doing something every hour instead of every day, or doing something every minute instead of every hour. This allows you a lot more power, a lot more time to get stuff done. So first, this is a hands-on. You don't have to do the hands-on. If you want, you can just watch along with Jupyter notebooks that are already prepared. And you can go to that top link, which is github.com/H2AI/H2O4GPU. If you want to do and you go to the link examples py demos. So I'm going to give everybody just 10 seconds to do that. If you don't want to do the hands-on, you can go there. You can do both. You can do both the hands-on and just view. But if you have problems with QuickLab, you might want to just look at these notebooks online. So if you want to do the hands-on, also please go to H2AI.quicklab.com, spelled as is, QWIKLAB.com. The first thing, if you haven't already done this, is you need to join. And when you join, you'll create an account with a valid email address. You'll receive a confirmation email. You'll click on the confirmation email. And then once you do all that, then you can go back again and log in. And then there'll be I'm already logged in. But once you are there, let's see how this is going to work. You'll see something like this, which will show on this top is a grid, and that's what we call a catalog. Under that lab, you'll see Introduction to H2O4GPU. You can go ahead and click on it if you want, but please do not, unless you want to have trouble, please do not click on Start Lab quite yet. If you do, you may run out of time before the end of everything. So if you want to follow along, follow that detail. Once we'll get along, we'll get to the point where we start things, and you've chosen this, and you start, it'll provide you in the upper left corner of this page, will pop up after you start lab and you wait for a while, it'll pop up an IP address, and you'll copy the IP address into your browser, and then you'll be in an Amazon instance, which will be the Jupyter notebooks. It'll be the same Jupyter notebooks that will be on the GitHub repository. Okay, so don't start lab yet. That's my main thing. I'll talk a little bit about what this whole project is first, and in the meantime, while I'm doing that, if you haven't signed up already, this will give you the chance to sign up for QuickLab. But just don't hit start lab quite yet. In the end, also, it'll be in a browser, which will be a Jupyter notebook, and it'll request a token from you. You'll need to put in a token of H2O. That'll be the token for the Jupyter notebook that you'll be using. And that, again, is not needed if you're on GitHub, only if you're doing the hands-on. Anybody have questions about that? Probably done this already at least 5 to 10 times. All right. So this is all about doing machine learning with GPUs. So there's a team of us who are doing this. We have Matush, Aaron, Navdeep, Rory, Karen, Arno, myself, and Steve Boyd and his army of students. Basically, we've been looking at this since around March and incorporating new algorithms into this tool set in order to be used not only by anybody, but also within our own products, like Driverless AI that you've seen before. Now, why do we do this? The question is, why would anybody want to spend so much time doing GPU stuff? It's fast, but exactly how should you do it? How should you create algorithms? You always have an API layer that you have to work with, and you've got to make the API easy to use or nobody's going to use this software, not even yourself. And the other thing is you've got to make it fast and useful, and you choose algorithms that will be very useful to customers and to our own internal customers like Driverless team. So how do you figure that out? Well, you can ask data scientists. and that's what Kaggle did about a few weeks ago, and asked them, what kind of machine learning algorithms are people using? And typically the response is like this. From about 7,000 data scientists, most of them are using logistic regression. You would think of that as a poor man's machine learning algorithm. Why, anybody want to throw out a response of why that is a typical machine learning algorithm? Yes? Yeah, perfect. Probably the biggest thing is explainable and it's fast. You don't need to have a lot of machine power to do it. And the same thing is probably true for decision trees. A little bit less explainable, but still somewhat interpretable, especially currently compared to neural networks. So, and this is not true for some groups. Military and security, their top is neural networks. But for banks and everything, anybody that needs explainability, obviously these simpler models are optimal. Now, there are, of course, many other things like neural networks that are used, and I can classify this somewhat arbitrarily into a group of algorithms which are classical machine learning, which I focused on in red, and deep learning. Now, this is somewhat of a misnomer. It's this completely arbitrary classification. People have arguments over this. For example, decision trees and random forests can be extremely deep, especially with some of the latest algorithms that I'll mention. They can go very deep and have very fine structures. So it's not like shallow versus deep. That's not the key criteria. The key is really just classical machine learning versus the more modern deep learning. But it turns out that machine learning, the classical kind, is actually what's mostly used by real data scientists. Now you could imagine, well, can't we just replace everything with neural networks eventually? That's sort of one vision. If we can get interpretability in there, maybe. And it's a work in progress. But for the time being, at least, it's not obvious that that will maybe even ever happen. At some level, interpretability is a challenge. Good interpretability is a challenge. And so having classic machine learning algorithms that we understand can be useful. Another question you can ask is, well, if you're developing an entire new algorithm, an API, et cetera, like we did for GPU algorithms, how exactly should you do this? Well, the top data scientist choice is Python. Anybody want to hazard a guess as to why people choose Python? Why would you choose Python? Anybody? You probably know the answer. Go ahead. It's easy to use. Yeah, if you're a data scientist, you want to prototype something quickly, it's a really good starting point. A lot of packages, very easy to use. C++ is awesome. It has a lot of capability, but it's not as transparent to start with. So that's why we're thinking about, when we develop things, we want to have an API that's Pythonic. And in particular, also very specifically, we want it like scikit. So scikit is this well-designed API and set of algorithms for machine learning, and we want to do the exact same thing on for GPUs. So the motivation is partially by Python and Jupyter Notebooks being very important, but of course it's also motivated by, and we want to also do R within our H2O4GPU, and this is partially motivated by this. It's also partially motivated by our own data scientists use scikit a lot. And we know that they're extremely slow. Often they're single core on a multi-core system. That's horrible. And they don't care about GPUs. If you ask them, literally you can ask them, and you can Google this, they don't want to do GPUs. And they don't really care about multi-core. So there's a huge performance gain just by going to multi-core. But if you go to the GPU, that's even much more gains. With GPUs, it's clear that there's a big shift, and this was talked about yesterday in one of the keynotes by NVIDIA. Basically, the point is that while transistor counts have been increasing, the performance of our computers have not. And this is saturated because you really can't do everything in parallel on a classical CPU. But with GPUs, it allows you to go much higher level, to do massively parallel operations. If you can find an algorithm that can be massively parallelized, it's perfect for a GPU. Not every algorithm is massively parallelizable. What that means, you have to be selective. You have to choose your algorithm that can be put on the GPU. It's not just willy-nilly. But if you choose some algorithms, and we'll look at a few, you can see massive gains. one of the reasons why there is such a difference, and this was also mentioned by NVIDIA, CPUs are great for low latency, and they can carry out very complicated logic, out-of-order speculative execution. Whereas GPUs are very good for high throughput, and they're tolerant to memory latency. You can overlap work, and you can, as long as you can find that highly parallelizable situation, they're really good. So H2O4GPU is the new product. It's open source. It's available on GitHub. Anybody can use it. Anybody can contribute. Please do contribute. It's used within our own Driverless AI product to speed up some operations by 30 times. Like, for example, if you run the entire Driverless AI product for some data sets, it will be 30 times faster on a GPU system than a CPU system. So that's a huge performance gain. It's scikit-like. As I mentioned, scikit is a very nice API. You basically have something like you have your model data set, you create a model type, you then fit your model, you can transform the model using that fit, and you can do predictions. So that kind of staged API is what we follow. We try to actually duplicate scikit identically. The good thing is we have scikit already in our package. Basically, we inherit all of scikit's CPU algorithms automatically. So if you want to run scikit, you can literally import H2O4GPU as scikit-learn, and you'll be good to go with all the CPU algorithms. And for most part, all the GPU stuff, if we have a GPU algorithm, it'll be used automatically. So we try to make that as easy as possible. Again, we don't import all algorithms. We choose selectively. Here's our roadmap, our plan for the future. So in our past, we've implemented several algorithms, including GLMs, linear models, which includes logistic regression. We have GBMs, of course, based upon XGBoost, random forests, and Kmeans clustering. And we've added recently PCA and SVD, and we can add many other things that we're working on. And we're working in this with a partnership with NVIDIA. So there's several NVIDIA engineers that are working to add some of these algorithms. So there's a good group of people working on this, good backing, good support. In the future, we'll be implementing many other things. This is more like a laundry or wish list, but as an example for time series, which is very important, a lot of the things you would do can be very fast on a GPU. Like if you're doing Fourier transforms, you can do that very quickly on a GPU as compared to a CPU. It's a really parallelizable operation. So that's our roadmap. And we're supporting projects like the Go AI project, which is with MapD. The idea is that everything should be on the GPU. You don't want to go back and forth between the CPU every time you do a step in your pipeline, because you're basically wasting time going on the PCI bus. So the idea is to stay on the GPU for as long as possible. Pass the GPU data between these different algorithms. And so we support that as well, which scikit, there's just no way to do that. That's one of the reasons why scikit's slow. Right. The other motivation is that Driverless is one of our internal products, and it uses many of these scikit-type capabilities or algorithms. And if you focus in on this variable importance in the center, this variable importance tells you what kind of transformations it's trying in order to generate new features from the original features. And it's showing you how important those generated features are. And if you zoom in, I don't know how well you can see this on the screen, but some of the top features sometimes involve cluster distance. What this means is it's taken these original columns of data or features of data, it's generated, say, 8 clusters from the stream of data, many, could be a billion rows, and taken it and reduced it down to only 8 clusters, and then found out for some cluster, it looked at the distance between the cluster center and all those points, and for whatever reason, that distance is a really good feature. So that's one thing that pops up. It is the highest important variable importance. So that means that if you can do K-means clustering fast, you get a fast overall product. Similar for truncated SVD. Truncated SVD, I'll explain a little bit later, is something where you're doing dimensionality reduction using something called singular value decomposition. It's a matrix operation. And Yes. Okay, push start now if you have quick labs. All right, thank you, thank you. I'll do the same thing. So before it goes away, go over to here and click Start Lab. And we'll get there in a second. All right. So truncated ASV is another feature, and it's basically dimensionality reduction. And we'll talk about that soon. And that ends up being one of the almost top features over here. Okay, so let's get into it. So Kmeans clustering. It's an algorithm that's based upon something NVIDIA prototyped, and we improved it to be much, much faster than the scikit-learn by about 50 times on average. Sometimes it could be 300 times faster, depending upon the data set compared to scikit, and I'll show that. It's significantly faster than other GPU implementations that exist. There's only one other that's really good. It has all these extra features that are in scikit that aren't in the other algorithms. Supports multiple GPUs with good scaling, and it can batch the process if you run out of GPU memory. Here's an example of performance metrics. You have, say, TensorFlow do the job of K-means clustering, and it's basically a contributed project in TensorFlow. And it can detect the GPUs, but it just doesn't really use them that much. It just uses mostly CPU for whatever reason, and it's extremely slow. For example, a typical Kaggle data set may be home. So this one's a home site, claims insurance, and it takes about 1,300 seconds to run on this particular model. You can do scikit, which doesn't do much better. So that kind of makes sense. TensorFlow and scikit, they're doing about the same job. But if you use a single GPU, we originally, say a few months ago, running in about 30 seconds. This is a huge factor boost. And now we recently improved it to be down to 10 seconds. So you can go from basically a factor of roughly 1,000 to 10, a factor of 100, roughly speaking, improvement in performance. And there's reasonable scaling with the GPU, although we're always working on those kinds of improvements. So this is a pretty amazing boost in performance. Partially the reason is because these are just inefficient algorithms. The basic point is that with TensorFlow, it's not really smart to use TensorFlow for classic machine learning. It's just not designed for it. And scikit is not smart either because it's single core, it's slow. It doesn't certainly support GPUs. All right, so let's look at one of the labs. So if you go over here, I'm going to take this link, copy it into a browser, another page. I'm going to insert the token of H2O. I'll save the password. And then we can go into demos. And the first thing we'll look at is this notebook. It's called H2O4GPU underscore Kmeans underscore images. It's a really simple thing to get oriented. So let's see how this works. All right, it's a long notebook. We'll go through it sort of step by step. What I would like you to do is go ahead and click Cell and Run All. So that it go ahead and produces the results so we don't have to wait every single moment for it to do something. It'll show you how performance runs as output, so you don't have to worry about that. That's a classic thing. You should always have a Jupyter notebook where you can just run all and see the results. Okay, so all it does is first chooses some imports that it's needed for plotting, chooses the number of clusters, there's 21 clusters. It chooses a file. Here it's going to be a cute file. It's, of course, the H2O logo. And what we're going to do to that logo is we're going to add to it, down here, we're going to take it and turn it into random noise. So you're going to randomly sample, essentially, from that original H2O logo. So now the data set is these yellow dots. So it's not the dense data set. It's a sort of randomly selected portion. And the idea is, how do we cluster this? So we still haven't hit H2O4GPU yet. This is just setup. So we're also going to ask, okay, how big is the data? It ends up being about, let's see here, 10 million rows, 3 columns, because there's 3 colors, RGB. Okay, here we go. Import H2O4GPU. And all it does is like scikit. You say, my model is H2O4GPU.Kmeans. Number of clusters is k, the number 21, with a tolerance of 10 to the minus 7. And then we time the fit on the data set. We do model.predict on the data set to get the cluster assignments. And then we report back what our cluster center locations were. Now, what I'll show first is just the result. And that's basically it. This little piece of code is all that really H2O4GPU is about. You have a model, you fit, you predict, and then you have extra information you can also access. That's it. It's very simple. It takes about a minute. The longer part is just to plot it. So this is just plotting stuff. It's nothing related to H2O4GPU. So basically, this is going to show the results of the clustering. And what you're seeing is the original logo. The noisy points were here, but now those noisy points were clustered. And the black dots are the centers of the cluster, and the boundaries are always the distance from a given point to the cluster. So this point here would be identified associated with this cluster. When you cross this boundary, it's because the distance has changed to be shorter to that cluster. That's all it's doing. Right, so why is this useful? It's a huge dimensionality reduction in some sense, a row reduction. You're reducing what used to be 10 million rows into maybe 21 clusters of data. And maybe, not in this case, it's just random, but in some data sets which aren't random, like the Driverless AI example I showed, this particular cluster may be an excellent feature. The distance to that cluster may be an excellent feature. And that's what you can use. Because of it being a larger cluster, or the distance somehow has meaning after you do a tree score, you actually build a tree model on it and it scores well. That's this whole Driverless AI pipeline. Right, so that's a very basic introduction to Kmeans. Any questions about that right now? Immediate questions, hands up? Yes? You can't see the image? Maybe somebody can help with that. Maybe Navdeep or Matush. Anybody able to get it to run? Some people? Okay, at least some people were able to get it to run. Okay, we're going to stick with Kmeans, and we're going to go to another notebook. This is this notebook called H2O4GPU, Kmeans quantization. Click on that. Once it loads, then you go Cell, Run All. And you may have to scroll back up to the top of the notebook, hit Home, or hit the side. These little side, I don't like Jupyter Notebook for this, but hit the side over here so you can get access to the broad window, and then hit Home and it'll pop you back up. Or you can use the scroll on the right. Okay, so this is just another example of how Kmeans can be useful. These are all fairly abstract. You have to sort of have an imagination slightly how you would apply this to a particular industry. My background is in academia. I was a physics professor, so I'm more of an algorithm guy at this point. So please excuse me if this is not the application you are interested in. Try to have some imagination. Right, so here we have color quantization. We're going to do some imports just like before. We choose, again, which data set we want. In this case, we're going to choose a data set. Let me show you this, sorry. We're going to choose a data set which will be shown below, which is basically a Chinese garden or a Japanese garden or something like that, which has a lot of interesting structure. So we still haven't started H2O4GPU. This is still just choosing data. The first thing we're going to do is we're going to run Kmeans on a piece of the data. It's a small piece of the data, and we can ask, okay, well, what were we doing? We import some cluster algorithm from scikit-learn called Kmeans. We say take a portion of the data and shuffle it. That's not too significant of an issue. And then we choose the model to be Kmeans with a certain number of clusters. Here we're going to reduce the original set of 65,000 clusters down to 64 clusters. So you can think of every pixel as a dimension, and every pixel has a possible number of values, and we're going to figure out in that high dimensional space, how do these colors cluster? And we're going to reduce the 65,000 cluster set to a small set of clustered colors and use those as a color palette of 64 colors. So here we took 24 seconds with scikit-learn, and then we're going to go down. And this is machine dependent, of course. And it takes about, with H2O4GPU, less than a second, 606 milliseconds. So that's already a factor of about 40 times improvement on a small data set. So let's actually look at it. Oh, and there's also, you can do one more thing, which is the dumbest thing you can do, but it can work sometimes, is that you randomly sample the color set in high dimensions. You don't do any clustering. You just randomly pick among the points of what colors you should use for those 64 colors. That's sort of the dumbest choice you can make. OK, let's look at the results. So let's see. Here we're just plotting, just a bunch of plotting routines. We'll just look at the picture. It's good enough. So here's the original image. Let me try to zoom in. So here's the original image. I think this is the one of the two gardens with a temple. So this is showing a lot of detailed structure. Sky is smooth, everything. Everything's really nice. And then if we try to do the fast thing of just randomly sampling, then you get something like this. Now let me try to pull this up together. I'm not sure if you'll be able to still see it very well. I probably should have put them side by side. I'll show a piece of it like this. If you can look on your own computer, what you'll see is that the structure in here, which is very nice and layered brown, has turned into kind of this weird green. It's not really, random selection is not the best idea. So clearly, some level of smart ML clustering of colors, some kind of smart quantization is better, should be better. And this is now looking at H2O4GPU, and it's showing that it took 0.6 seconds to do a portion of the data, and it looks good. It doesn't have the errors in this little kind of region or errors anywhere else. So it's a good clustering. So it's better than random. And it doesn't take much longer. It's 0.61 seconds. But if you were to do scikit-learn, it takes 24 seconds. So that's a lot longer. Now let's do the exact same thing on the whole data set. So this is exactly the same, but we're not doing that skip factor that was in there before of it's just not skipping any data. And so H2O4GPU takes about 730 milliseconds, or 1 second. That's the result for the whole data set. Here, 0.73 seconds. scikit-learn on the whole data set takes 220 seconds. So that's about a factor of 300. So going on the GPU, doing clustering, which is an important element of driverless AI in many machine learning algorithms, is about 300 times faster on the GPU than scikit. So you can see that this has to help. It can't be trivial that you get such a performance boost. Now, the performance boost is dataset dependent. It's size dependent. It's dependent upon a lot of things. But this is the kind of performance boost we get here. Any questions about this particular demo? Is everybody able to run it? Anybody more or less ran it? It kind of ran and didn't crash? That's good. OK. So now let me go back to the talk. All right, so here's that was the classic Kmeans benchmarking. This is a different home insurance claims predictions data set. It's not a pretty picture, so it's harder to see, but you can see that the scaling works for real data sets too that you might care about in your industry. OK, let's look at another algorithm, which is PCA, principal component analysis. So this is obviously just taking a data set and finding out which directions are the most important. The first principal component is that one which has the most dispersion, which explains most of the variance in the data. The second principal component explains the next most important variance in the data that's orthogonal with that. And it can do any kind of affine type transformation. You can do rotations, you can do scaling to sort of fit the data with each one of these components. So let's look at a particular data set. So again, this can be applied to any industry, but this is just a cute way of seeing it. So this is called the faces data set. There's a lot of faces here. You can see they're already pretty creepy at this point. A lot of weird faces, but they're just normal human faces, trust me. To use PCA, you have to take these faces and so-called center them. You have to remove the average face from all these. Then they look like this, which is even creepier. You start to get weird, when you de-average somebody, if they're not very pretty, perfectly pretty people, I guess, are more averaged, more close to the average or something. They get pretty ugly. The deviation is ugly. And then you can say, well, you can actually, and I'll show the notebook, you can actually generate faces from a reduced dimensionality data set. So basically, what we've done here is taken the original faces, which is a huge number of them. Every pixel in this image represents a dimension. There's like something like 64 by 40 dimensions, 2,000, 3,000 so dimensions. And we're going to reduce that down to 150 dimensions. Super compression of the data set. And then you end up being able to regenerate the face from those principal components by transforming the data, and you get something like this. These kind of generated faces from a reduced data set. So let's actually look at the notebook. So we're going to go back to Quick Lab, and we're going to go to PCA. So this is H2O4GPU _ PCA in the list of notebooks. So we'll click on that. And once it's ready, then you go to Cell, Run All. And again, click on the right or something and click Home so you can get back to the top. So the only thing I'm going to show on this one is there's multiple types of experiments in this. I'm only going to show one, the faces one. So if you go scroll down, there's many experiments here you can browse in your own time, digits, etc. So this is basically an scikit-learn data set called, well, it's related to something you could say is an eigenface. Principal component analysis basically reduces the dimensionality by finding those principal components. If you find 150 principal components out of the original huge dimensional space, then you can imagine reconstructing the new face again by adding up each one of those components with a different coefficient. And those coefficients are the learned weights for that particular face. So you can imagine building up any face by first taking the face, finding out what those coefficients are, projecting those principal components on those coefficients, and getting back the transformed face, or say inverse transformed face. Okay, so let's do that. So there's some kind of number of people here. In this case, it's Bush. What are the names? Yeah, there's like Bush and Colin Powell and people like that. Al Gore. I see Al Gore. Who do you see? Okay. Yeah, up in the top right. So we're going to take this a huge number of faces, just a sample of them at different angles. Scroll down. We're first going to take the model called PCA H2O4, H2O, say we want 150 components, and that's going to be our model. The model is simply we want 150 principal components. We're going to take the data, fit on the data, the whole data, and extract what are the principal components for the entire collection of data so that we can regenerate that data set arbitrarily. And then we can print out first what do those principal components look like. Not just to regenerate the faces, but what are the actual, after we've fitted the data into components, what does each component look like? You can visualize it by just transforming, say, one weight times that component and do an inverse transformation. So these are principal component faces, or so-called eigenfaces, because they're kind of like eigenvector, eigenvalue decomposition. So this face would be like a dark face, maybe. This would be a light face. This is a shadow on a face. These are dark eyes. There's different kind of structures that are principal components of our faces that it's picking up on. Key thing is, of course, these are linear additions. So you're linearly adding these kind of eigenfaces. It's a linear, this process of PCA is a linear process, not nonlinear. So we have all these transformed faces, and we end up we can do the inverse transformation. This is just, I should show the code. So we can fit, we can transform to get components on the data, and then we can do an inverse transformation of the components back onto their projected space, and then we can look at, from the original faces, how can we reconstruct from their weights the faces from those principal components. So you can see here, I'll show a little bit further. So you can see here we have the original faces, and these are the reconstructed. It's not meant to be very accurate, of course, because we only have 150 dimensions out of the 2,500. That's a huge reduction, a huge compression in the amount of information you need. For 150 dimensions, you need 150 numbers to describe each face. The original data is around 3,000 numbers to describe each face. That's a really good reduction. So that's the point. And you shouldn't think of, oh, I can only apply this to images. Deep learning can do this very well, too. This can be applied to any kinds of data sets that can be turned to numerical data sets, like in Driverless AI. So it can be financial data, any kind of weather data. It doesn't really matter. And it can do that dimensionality reduction. OK. So I think I have a little bit more time. So I'm going to go back to my talk. Now, you'll probably have nightmares from some of these faces, but please don't sue me for it. The kind of performance, I didn't really talk about performance with this algorithm, but it's good. So with scikit-learn, the time it takes to do certain kinds of matrices with some number of reductions in dimensions, like dimensions 100, going to dimensions 100 from an original of 10,000 with 100,000 rows of data. It takes scikit-learn about 700 seconds and H2O4GPU about 100. It's about a factor of 7. And we just started this algorithm recently. So this is easy gains on the GPU. As we improve over time, we improve these algorithms, not just by a factor of 50%. We find ways to improve these things by factors of 5, factors of 10. So we're always improving these things. OK. So the next thing I want to talk about, the last thing I want to talk about is GBMs. This is sort of the key thing inside Driverless AI. There's lots of feature generation, but how do you know which features are good? You need to score them somehow. And we use trees, GBMs, to score them inside Driverless currently. A GBM, or a gradient boosting machine, is simply some kind of decision tree-like structure which figures out in the top, what is the optimal way I could choose where to split the data point from a bunch of data, say 0 to 1, or take age. Say if I have ages, if I want to try to ultimately decide who gets cancer, or what kind of ages drive cancer, should I choose to split from between ages 1 to 2? Probably not. It would be something higher up. And so this makes that decision of what's the optimal splitting right away to predict who gets cancer. And then it can figure out, oh, now that I've done that, how do I make another split, et cetera. So it keeps on partitioning the data until it figures out how to optimally predict the target. And this algorithm's been improved over time by Rory Mitchell significantly. He's the person that created the GPU version of XGBoost, which is what we're using. I won't talk about the details, but it's multi-GPU. It has highly efficient compression of the information before it sends it to the GPU, so it's very fast. It handles sparsity very well, all these things. I just want to mention one thing about it, the GBMs. There's kind of two classic ways to grow a tree. One is so-called Levelwise growth, where you split every single time. You always find the optimal splitting, but you never decide not to split. You always split in trying to figure out how to grow the tree. There's also so-called leaf-wise tree growth. And this basically says, well, I don't need to always split. I choose the split whichever will be optimal for the loss function I've chosen. So it's not going to be based upon, well, where's a split that I can choose? It's going to be based upon the optimality of the loss function. OK. So these are also our high-performance algorithms on the GPU. On a typical, says that, say, 2 Xeons? Yeah, 2 Xeons. It takes about, for a given data set, which may be the Higgs data set, it's just an arbitrary data set, trying to discover certain particles, figure them out in the data. Binary classification problem. It ends up taking about, I should say the data size, 29 columns, 1 million rows. And we're doing this on a large sample of depths of the tree, and we're choosing different kinds of sampling of the data set. So, variety of options. And it runs about 1,700 seconds on the CPU. And originally, we had about 400 seconds on the GPU, a single GPU. And for the same GPU, we improved that to be about 170, and it's probably even faster now. And it has scales pretty well. So this is running in sort of embarrassingly parallel mode. This is running on all the GPUs, each GBM at a time. Why do we do that? Why is that fair? Well, Driverless AI does exactly that. Every time it needs to score a given data set with new features, it actually puts it into a GBM and figures out which one is the best score. So it will score a bunch of different sets of features, and out of all of those, each one of those will be scored on a different GPU. So every GBM is on a different GPU. And so that's why this is a useful way of doing things, because it will show us that there are no bottlenecks whenever you do that kind of thing. We can also do this with a single model on multiple GPUs. And we're all constantly improving that kind of capability to get good scaling. OK, so the very last demo, if you go back to the demos quick lab page, and we're going to go to GBM. That's called H2O4GPU underscore GBM. And you do cell run all. So this is, I should go back to the slides to show you what this is about. So this is just an example data set from Kaggle, where it's showing you have some map of data, and what I've given you is cartographic information. Like, for example, the slope of the hill over wherever you are, the distance to a water supply, a bunch of kind of information. And I've also told you the type of, say, grass in the area. All these kinds of things. And from 54 different features, you're supposed to predict what type of forest cover is there. Because we don't have satellite data for all that, but we do have a lot of cartographic information, local information on the land that was taken. So you don't want to do satellite imagery every time. And so this is just a multi-class problem where you have, say, 8 different classes of covers of the forest, and you're trying to predict which one it is from a given training data set from 54 different features. OK. So going back to this notebook takes a little longer in the very end, and I'll explain why. It's scikit-learn. So here we get the data set. Fetch cove type is a scikit-learn import. We split the data in train and test. And then we set up, we load the data into XGBoost. This is called through a D matrix kind of data set form. We set the parameters. This is going to be using, by default, what's called GPU hist. Basically, it's a histogram method. As opposed to having every single value in the data set, everything is binned into histograms first, say with 256 bins. And we operate on that. That reduces the data set quite a bit. And it also makes it much more efficient for an algorithm. This is so-called a growth policy of depthwise. This is the version where you split every single time, as opposed to loss guide, which is a different one I'll show. The objective is multi-softmax with num classes of 8. It's a multi-class with 8-class problem. And the rest of these are other kinds of parameters. So the very first thing, I'm going to make this a little smaller so I can see everything. It's more or less, for this one, showing big plots or the numbers. So this is GPU hist depthwise. And it took, for this problem of training this multi-class problem, about 6 seconds. GPU hist loss guide, the one that you can go down without having to split. You can go down deeper, a deep tree without having to split. That also takes about 5-6 seconds. In this case, scikit-learn's version of depthwise takes about 22 seconds. So it's about 5 times faster on scikit-learn, on H2O4GPU. Same thing with the loss guide. It takes about 23 seconds. So it's slower, for sure, by about a factor of 5 using scikit-learn. That's already a good boost. I'm going to skip this. You could use a so-called scikit-learn type API for this. It's also the similar speed improvement. I'm going to go scroll all the way down to this showing off of feature importance. So we're going to do now a much more number of trees that are built on top of each other. The way the GBM works is you build one tree, and you don't build just a duplicate tree. You try to build a new tree, which is an improvement on that prior tree. And then the next tree you build is an improvement on that. It's a cumulative improvement of trees, of decision trees. So in this case, we're going to be using GPU Hist loss guide. This is the one that goes deep and it doesn't have to split. And we're going to go allow for a total number of leaves, total little number of nodes of 2 to the 6. And we're going to see how that works. So this will run. It runs and runs and runs for 200 rounds, 200 different trees being built. And it's showing you this happens to be the training log loss. This is actually training error, and the smaller the better. And this is the validation on the test set. We don't touch the test set to train, but it's just showing you, evaluating for you how it's working. And it takes about, for this one, takes about 1 minute and 55 seconds. And then we can do some analysis. We can first show you the accuracy is 90%, which is pretty good. We can show you how the train and test error scale with number of iterations. So you can see it starts off at high error and goes down to a small error, about 20%, or log loss of 0.2. This is an interesting metric. It's called feature importance. If you just basically count for a given feature, 54 features originally, and you count for a given feature, how many times did it split in the tree for every single one of those trees that were being built. This is the score. And so this particular one, you can probably barely see, F5, is some, like, it's the grass happened to be green, and that's a really good way of predicting the forest type, the tree type. So you didn't look at the satellite data, but you just look at the cartographic information to deduce that. So that says that you don't have to go do a satellite investigation. You can just use people running around on the ground to figure out, ultimately, in more general areas, what the cover type is. There's another kind of variable importance, which is the next version, which basically says, it's a little bit of computation, but it basically shows you here, it's not just how many times it split for a given feature inside one of these trees, it's how much gain did that give you to split for each one of those splits for that particular feature. The gain would be how much did it reduce, for example, the loss function, the error in the loss function, or the log loss in the loss function. Okay, and there's other things I can talk about that. The last thing I want to mention is how does scikit-learn do with that? We said H2O4GPU was about 1 minute. Well, we're not even done. It's still computing here. It ends up that it takes about 30 minutes. So it's about a factor of, for this particular case, probably about a factor of 10 to 20 times faster than doing this on the CPU. This is not scikit versus H2O4GPU. This is H2O4GPU versus itself. It's the CPU version versus our GPU version. And the CPU version is the classic one. It's the open source XGBoost. So it's just showing you that the GPU itself can give you, with simple data set, but complicated problem, it can give you a boost of about 10 to 20 times, no problem. It's not always that way. Sometimes it's 5 times. On the Higgs data set, it's more like 5 times. On other data sets, it'll be even more, like 40 times. But this is an example where it's about 10 to 20 times faster on the GPU. And this is just a single GPU versus all the cores on a given CPU system. Okay. Any questions about that particular notebook? Was anybody able to run it? Yeah, I saw a few hands. Okay, good. All right, let's go back. Okay, basically done. Please stop your labs if you've done. Please go to the website, H2O4GPU at H2O.ai. Check out our Gitter. You can ask any questions you want. If you have problems installing it, etc. You can also go to Stack Overflow and ask questions. I'm happy to take questions now on Slido. Thank you. Well, H2O4 GPUs support multi-core CPUs. Yes, it uses scikit-learn by default, and some of those algorithms, most of them don't support multi-core. We do have some algorithms that are both GPU and CPU on our side, and that's a very good point. We're looking into supporting more of the CPU side as well, but our main focus is on GPUs because of the massive performance gains that you can get. But yes, that's something we'll come back to as we move along. When is nested CV coming to H2O? Is that an H2O4 GPU specific question? I'm not really sure. Yes, some of the algorithms, like our GLM algorithm, which I didn't have time to mention, that Sri showed. He showed this two-panel thing of CPU versus GPU with all the data, the models being filled. He mentioned in his keynote, does use cross-validation, but this particular question is more broad than that. Let's see. Does AutoML work with H2O4 GPU? It's on the roadmap. It is on the roadmap in the sense that some of the back-end stuff that AutoML uses should use, like, say, the XGBoost GPU, and it's not currently, which is part of H2O4 GPU. So yes. Let's see. Are there any plans to put H2O4 GPU in H2O3? I think the goal of H2O4 GPU is to be all-encompassing, to really replace H2O3. So that's why, yes, it is important that we support CPUs. But we're not going to be trying, unless somebody says, oh, we're a customer, we need it, we're not going to be trying to focus on integration with H2O3. We'd rather trying to ultimately replace it as a product at some level. But there probably won't be perfect, right? Some integration will probably occur. Let's see. The performance gains. Would I see gains in H2O on a commodity laptop without a fancy graphics card? That's a great question. So right now, this is mostly supporting NVIDIA's GPUs. That's one point to make. So if you don't have an NVIDIA GPU, it won't work. The other point is most consumer products on laptops, if you get a generic laptop, even if they're NVIDIA GPU, they're probably not the fastest. There's some mobile version. But often the CPUs aren't very fast either. So it'll probably be balanced out. And I can't tell you for a given, it would have to depend upon the data set, the algorithm, et cetera. K-means, you're probably going to see the boost compared to scikit. SVD, you may see a boost, it may not be as great. GBMs, you may not see as great. So this K-means is probably an example where you would still see a good performance boost with a generic NVIDIA GPU on your laptop. Let's see. Will H2O4 GPU, so other than, that's a great question. So our ultimate vision is to support as a back-end, anything like TPUs from Google or any kind of other hardware. And so we're trying to work that out. And basically, we hope to support any back-end, but it's a challenge at this moment because the hardware manufacturers need to also support some at least primitive layer themselves. We can't develop the entire hardware stack with only 60 so people. Is this clustering based upon 3D RGB space, or if not, how is the distance matrix calculated? So yeah, so it ended up, I didn't clarify this much, but it's really only basing upon one color. The other colors are ignored, so it's really just one type of color that's in the end important that's used. And as far as how the distance matrix is calculated, it depends upon what you're saying. If you mean the pairwise distances between clusters and points, that big matrix of cluster versus which data point, that is done in two different ways. One is just using a matrix multiply operation that is built in the CUDA. And another way is Mateusz and others develop for small enough data to reduce this down to a built-in our own CUDA kernel. So it's different kinds of operations. All just matrix operations ultimately, though, yes. Would this be released to be used in R? Yes. Aaron, one of the people I mentioned, is going to be porting this to R. It's just a question of how and human resources. Is there a way to keep data on the GPU between model runs? Yes, that's a great question. So we have support for this Go AI project. And basically what it means is that we have not only the standard scikit looking like kind of way of doing things with fit, predict, transform, we also have versions which look like fit PTR, standing for pointer. It's a really bad name, we can change it, and transform PTR, predict PTR. These are the ones that pass in GPU data pointers, and you can pass them between. And you can use our algorithms and piece Kmeans through to, say, truncated SVD through some of the other algorithms. Now, right now, that's not always true. For example, XGBoost doesn't support that yet, but we're in serious discussions to do that soon. The hope is that all these algorithms can communicate directly being on the GPU and stay on the GPU. So that, and for driverless, this would be amazing. In driverless AI, what we do is we constantly go back between the CPU and GPU. And this is really not necessary. You could stay on the GPU. All the feature generation could be on the GPU. All the scoring could be on the GPU for trees. All the feature generation, like clustering, could be on the GPU. And it would be a much faster product. And this is our vision. I'm confused about which GPU-based algorithms in H2O4GPU, I guess, about which ones are GPU-based and which have been pulled into existing libraries, XGBoost. Yeah, XGBoost is the primary one. You could say really it's very similar to the original XGBoost with some improvements. For example, it handles the Python data table as an ingested product, which is part of Driverless AI. But in reality, all the other algorithms, there's some algorithms which are from NVIDIA, other open source projects for, well, there's the original CUDA stuff for SVD. So this is sort of homegrown in some sense. We've taken multiple packages, put it together, and we have taken XGBoost and created wrappers that allow it to look like scikit as well, and more directly like scikit. But yes, it's a great point. XGBoost is the most pure of a separate thing. The other algorithms are more our own. But we're working with people like Rory Mitchell, who is the developer of the XGBoost version, of the GPU version of XGBoost, and his collaborator, Philip Cho, who's doing the CPU side of XGBoost. And they're part of our team to continue that work with XGBoost. I've contributed myself to XGBoost. So we consider these open source projects as part of a community effort. And this H2O4GPU should be thought of that same. It's part of a community effort of doing all this stuff. We hope that anybody as a community could join the project. Does H2O4GPU use scikit-learn standard syntax for cross-validation? That's a great point. Some of the algorithms we have implemented, for example, cross-validation in the way that scikit does it is not exactly the same. So we're working towards that kind of API. Let's see if what the time is. I have till 4:25, is that right? As I understand, the fitting process of oh, that's gone. Oh, there it is. As I understand, the fitting process of GBMs is done serially, tree 2 after tree 1. Can you please elaborate on how it's actually sped up parallel on GPU? Yeah, so basically what's done on the GPU is figuring out what the optimal split is from all the histogram data and all the feature data. Where should I split next? And it's a huge amount of data that you have to race through in a certain way to figure out where the optimal split is. And then you have to deal with all that histogram data in a way that does the correct version of the splitting, what the loss function is, what gain will I get, for example. How should I split? So yeah, all those kind of operations are done on the GPU, while every iteration comes back from the CPU to the GPU for every step of building a new tree. Yeah. What is the process for parallelizing construction of a single GBM? Is it just distributing the columns for candidate splits across different GPUs? Oh, that's great. So currently, we've explored both, but currently the mode is that it just shards the row data. So basically, every GPU will have a portion of the histogram binned data set. And we run through that, find the optimal split on each GPU the same way, and then we collect that histogram data together. What is the difference between the H2O4GPU Elastic Net and H2O4GPU Elastic Net H2O? Yeah, that's a great question. So we have our own algorithms, which are often much better than scikit in a non-trivial way. So we want to expose both our underlying algorithm, which would be the H2O4GPU.ElasticNet H2O And then we have a wrapper, which is the first one, which decides whether you should use scikit-learn or ours, our H2O1. And that's decided based upon, we automatically choose the GPU if we are capable of handling what you told us to do, like we have implemented all the features necessary. Otherwise, we go to the scikit one. Basically, that's it. And we'll tell you. We'll tell you if it's scikit. We have attributes that are set that tell you what backend was used, all that kind of stuff. Technical aspects of parallel processing in H2O4GPU. For GPUs, same as splitting across machines. For GPUs, same as splitting across machines. I can't quite figure out what that means, but basically the different algorithms do the multi-GPU in different ways. There's mostly sharding by data. And on each GPU, it's not doing like parallel processing on the GPU by sharding the data again. It's different modes of parallelism at different scales, I would say. That would be the best answer, if I understood that question correctly. Okay, is that it? Okay, thank you, everybody. Thanks for coming.